This is Lab 3 on finding the mass of a black hole through the analysis of the motion of an orbiting star. So the explored problem for this lab was to find the mass of a black hole only through analyzing the motion of a star in orbit around it. Now we wanted to know how Newton's second law and Newton's law of gravitation could help us analyze this motion and find the mass of the black hole. To do this, we first analyzed the motion of the star and calculated its momentum and net force acting on it. By then rearranging Newton's law of gravitation, we found that the mass of the black hole is 1.9999 times 10 to the 31 kilograms. To explain how this value is found, we first begin with the given values. We are given a star with a set mass of 1.989 times 10 to the 30 kilograms, as well as a file of its x and y positions over time. Now we know that delta position over delta time equals the velocity. So now we can calculate the velocity of the star at any given point. But how does this help us find the mass? Momentum is calculated by multiplying the velocity by the mass of the star. Since we now have the velocity at any point in the orbit, we can calculate the delta v, then allowing us to calculate the delta p with delta p equals mass times delta v. Since we now have the change in momentum, we have a new way to calculate the net force acting on the star by the black hole. And how we do this is by manipulating Newton's second law by starting with force equals mass times acceleration. We break down acceleration into its components of delta v over delta t. Now we have the equation F net equals mass times delta v over delta t. Previously, we just found that mass times delta v is equal to the change in momentum. So we substitute this value of the change in momentum in for delta v times the mass to get the final equation F net equals delta p over delta t. The last unknown needed to use Newton's second law of gravitation is the distance, which we calculated by subtracting the final position of the star from the given black hole's position, which gives us a new vector pointing from the star to the black hole. So now that we have all the necessary values to use Newton's law of gravitation, all that's left to do is plug in these values. So we're left with the equation, the net force, magnitude, over the gravitational constant times the mass of the star, all multiplied by the distance squared, equals the mass of the black hole, which gives us the final value of 1.9999 times 10 to the 31st kilograms. So now it's important to see how Python can help us calculate the mass of the black hole and visualize the motion of the star. Now the velocity is calculated in this loop by taking the data from the CSV file to find the delta x and delta y, which are calculated here by taking the x position at the current index and subtracting it from the x position in the next index. The same can be said for the delta y. These values are then put over the delta t to get the x velocity and the y velocity, which we could then use in the next loop to calculate the momentum. Now as you can see here, we have the v initial and v final, which are taken directly from the table. The p initial and p final are calculated using this velocity initial and velocity final multiplied by the star's mass. Now these values are then subtracted to get the delta p, which we can then put over delta t to get dp dt. And as we discussed earlier, our net force is equal to this value of dp dt, which we set here. Now as you can see here in the code, we break down the force into two components, dp dt parallel as well as dp dt perpendicular. Now the reason we find these values, even though they're not used in finding the mass of the black hole, it helps us show how the black hole has an effect on the star. And this can be seen when we actually run the program. Now in this case, the red arrow represents the net force acting on the star, whereas the black is the parallel force and the blue is the perpendicular force. Now as you can see, the parallel force is always parallel to motion. And this is because it represents the speeding up or the slowing down of the object due to the force. The perpendicular force represents the change in direction. So the reason we break it down into two components is so that we can see which force is actually changing the velocity object and which force is actually changing its direction. So by using Newton's law of gravitation in the code, we did come up with a mass for the black hole that was quite accurate to the calculated value. However, with the way we calculated the mass, there are some problems which we can discuss in the what if question. So the flaw in our calculation can be seen when we answer the what if question. What if we had a new black hole? Would we be able to tell that there was a difference in the mass? Since we are only basing the net force acting on the star based on its motion and its momentum, we would get the same net force, same distance, and the mass would remain the same, meaning that when we use Newton's law of gravitation to calculate the mass, we would come out with the same value. And thus our program with the given files will only calculate one single mass of a black hole of 1.99 times 10 to the 31st kilograms. So what does it mean? We know that Fnet equals dp dt, so Fnet perpendicular parallel must equal dp dt perpendicular and parallel. However, even though they're equal in magnitude, they are different in their calculation and observation. We know that the force is what is actually acting on the object, but it cannot be observed directly, but the changing momentum can be, and we use this to calculate the net force. In the end, the Python program did do a good job at calculating the mass of the black hole as 1.9999 times 10 to the 31st kilograms, but it's limited by the fact that we only observe momentum of the star, meaning we only get one value for the mass. Overall, we were successful in utilizing Newton's laws to calculate the mass of a black hole solely based off the motion of an orbiting star.